Good day, everyone. I'm Crisron Lucas, and I'm here to present our short paper entitled Improving Long-Term F0 Representation Using Post-Processing Techniques. And my co-authors are Diptasree Debnath and Andrew Hines, who is also my supervisor. I'm from the School of Computer Science in University College Dublin. Okay, so here's the outline of my presentation. So let me begin with introducing you to F0, or I know most of you are already familiar with F0, or the fundamental frequency, which is a representation of our how the vocal folds vibrate, and also it also represents the pitch and the intonation of our voice. Now let me differentiate it with a long-term F0, which is F0, which is extracted from long segments of speech instead of short time segments of speech. So if some of you are familiar with this figure on the right, which is in Pratt, so we can see different contours of the fundamental frequency when we do analysis like autocorrelation for determining the F0 estimates of our speech. Now, as you can see, all of the speech and utterances have different contours or intonation, but for long-term F0, we're interested in representing this entire utterance with a single value or a single representative value which represents the speaker voice. So we use the term long-term F0 for that, and it has some applications, especially in forensics or representing different speakers, especially when you use text-to-speech, which are controllable as well. So you can also designate your F0 parameter for your speaker voice in synthetic speech. Now, there are lots of F0 estimators. I've categorized them into three, like if you're familiar with the autocorrelation base. So in autocorrelation, you just multiply a signal to a time-shifted version of itself, and at different lags. So when you determine the product with the highest the product with the highest value, it will correspond to your fundamental period. And you can also get the fundamental frequency using spectral analysis by means of peaking across the spectrum. And with the advent of different labeled datasets such as MIR 1K or StemSynth or MDB datasets, these machine learning methods have started to being developed. So like CREPE, MFPAM, and SPICE. So you can see in the figure on the right the examples of estimates of different popular F0 estimators. So pYin is autocorrelation based, Swipe is a spectrum based, whereas the other SPICE, CREPE, and F0 are machine learning based. So Reaper uses cross correlation as well. So as you can see, they have different estimates, and especially pYin, you can see some of those highlighted in red, some F0 which are detected at very high frequency values, which are of course misdetections because our voice only ranges up till 1K or less. So there are problems when using these F0 estimators for extracting the long-term F0 estimators. So aside from these F0 estimators having their own inaccuracies and variabilities, getting the long-term F0 by using mean or median or base values could also lead to errors. So there are some previous works that already conducted long-term F0 calculations by using the mean F0 of autocorrelation method, specifically on Pratt. And there are also other distinct works on using the median and base values. So the base value is a value that is 1.43 standard deviations below the mean, which was defined in the paper of this author. So these are the previous methods before that were being used. Now, as I've mentioned, there are already high variability and errors using the state-of-the-art and the popular F0 estimators. And using mean on that, especially when you have high frequency misdetection, would lead to an estimate that is not robust or inaccurate as well. So in this paper, we're trying to use post-processing techniques. There are three identified techniques. One is the median. There are previous works that also did median for modeling voice, especially on duration and intergender rankings. And the next one is applying thresholds. So pYin and Reaper already has a threshold on their own, but the other techniques still don't have these thresholding. And also another idea is to use time series smoothing, because F0 contour is a time varying waveform, and if we want to represent a more consistent and a better representative LTF0 or long-term F0 value, maybe we could apply temporal smoothing on the signal. So for the methodology, I scope my work with 6 popular F0 estimators. So pYin, Swipe, Reaper, FCN-F0, CREPE, and SPICE. So 1 autocorrelation, 1 cross correlation, 1 spectral, and 3 machine learning approach. And then I used 10 English speakers from the dev clean of LibriSpeech. So each of the speakers have more or less 10 minutes of speech data. And I made it balanced with 5 male and 5 female speakers. And then I applied these post-processing techniques from the dataset, from the F0 extracted data from the dataset. And then I evaluated them using the mean absolute error and the mean absolute deviation. So first is, let's talk about thresholding. So I tried to optimize the threshold parameters, and how to do what I did to do that was first plot a histogram or observe values for the ranges of the probability scores or the confidence scores. So pYin has also a voice probability scores when you use this algorithm. CREPE and SPICE have confidence scores. Swipe has pitch strength values. Reaper has correlation scores, and FCN F0 has periodicity scores. So looking at the plot on the left, we can see that CREPE, FCN F0, SPICE have a bimodal distribution. So maybe we can find an optimal threshold value within these peaks of values. So the ranges are quite different. So some ranging from 0 to 1 and some ranging from 0 to 1.2. And for Reaper, it's 0 to 1. And I tried to plot the mean absolute error across changing this in the range of these values. So I did this experiment, and I noted different optimal threshold values. More so if you change your data set to just the 5 male or the 5 female, I've noticed that the optimal threshold values for pYin actually changed. So for the male and the combined male and female, it's more or less the same optimal threshold values, like 0.5 for CREPE, 0.95 for Reaper, and 0 for FCN-F0. And I observed that the pYin is not robust across varying data when you try to threshold it as compared to the other estimators. Now, after getting the thresholding, I applied the median as well as the temporal smoothing. So for the time series smoothing, I used Kalman filter. And then these values now that are presented here are the mean absolute error values. So I tried to get the mean absolute error with respect to a manually labeled ground truth. So each of the utterance of the speakers have F0 or long-term F0 estimates, which were subtracted from the ground truth, and then I've averaged it across the utterances for each of the speakers, and then I observed it before post-processing and after post-processing. So what you can see on the graph on the blue is the mean unprocessed, whereas the orange represents the median post-processed uh, long-term F0 mean absolute errors. So of course, the lower value is the better. So as you can see with the blue ones, the Reaper is already good on its own without post-processing. But when you do post-process, CREPE performs at par with Reaper. And as you can see, SPICE has also low MAE value as well, whereas pYin has the highest uh, uh, MAE when post-processed. So summarizing this figure, without post-processing, Reaper performs best, followed by SPICE and FCNF0. And using post-processing, CREPE performs at par with Reaper. But as you can see here, a notable observation is that when using the post-processing techniques, the mean absolute error of Reaper actually worsened in performance. I also tried to get the mean absolute deviation to observe how how the variability differs between the algorithms before and after post-processing. So these are all delta MADs, so before post-processing and after post-processing. And what you can see in the values are also in the average MAD are all delta. So if it's negative, then the variability increased, and if it's positive, the variability decreased. So as you can see, CREPE and pYin benefited most with the post-processing, and only FC and F0 worsened in terms of the mean absolute deviations. So this table here are across the different 10 different speakers with the 6 different algorithms. Now I extended my work to checking the intergender rankings. So for the intergender rankings, you can see that after post-processing, you can clearly distinguish the male and the female speakers. And I also tried to check the Spearman rankings between CREPE Reapers, between the pairs of the algorithms. And you can see that the median post-process yields a more consistent rankings in terms of pitch with regards to, especially with CREPE, Reaper, and SPICE, as well as Swipe. So these CREPE, SPICE are both machine learning algorithms. Reaper is cross-correlation, and Swipe is spectrum-based. So in conclusion, the main takeaways from this study is that, well, if you're trying to measure your long-term F0, Reaper and SPICE are already good F0 estimators, and pYin is the least accurate. But if you use post-processing, it works best with CREPE, and with post-processing, you can have a more accurate long-term F0 and a more robust variability with respect to different data set. But of course, we're with some exceptions. So Reaper didn't improve in terms of accuracy, and F0, FC and F0 did not improve in terms of the robustness. So for future work, I suggest to do more ablation studies and try changing the filter parameters and adding more different experiments, as well as exploring other smoothing techniques. And for my future work, I'm testing this out for prosodic analysis of natural and synthetic speech. So yeah, that's all. I'm now open for questions.